So when we look at this one, the correct answer was negative 79 degrees Celsius because we calculate 194 Kelvin, and when we convert to Celsius, we have to subtract, and we do need to stop in the ones place. So make sure you're paying attention to your sig figs. So now we have looked at the three individual gas laws. And with the individual gas laws, we said, well, we can look at any two variables, and we had pressure volume if we were holding temperature constant and we were holding the amount of gas constant. We looked at volume temperature where we held the pressure and the amount of gas constant. And then we looked at pressure temperature where we held volume and the amount of gas constant. In the combined gas law, we can actually put all three variables together, and we still hold the amount of gas constant, but now we get 6 variables instead of 4. So the combined gas law looks like this. P1V1 over T1 equals P2V2 over T2. So I've essentially combined them. If you just look at the top, you see Boyle's law, P1V1. If you just look at pressure and temperature, you see the law of Gay-Lussac, and if we only look at volume and temperature, we see Charles' law in there. So it makes sense that we call this the combined gas law. What I found when I was a student, the first time I was learning this, I just got mixed up sometimes. Is it pressure times volume or is it pressure divided by volume? Because they're different. And I learned a little trick for the combined gas law that helped me with the individuals too. And it's kind of silly, but peas and veggies on the table. So you have pressure times volume and then dividing because it's on the table. So peas and veggies on the table. Where that helps. And I thought it was kind of weird because when I first learned it, I still thought a pea was a vegetable. But now I know peas are legumes, and that doesn't count as a vegetable. So we now have an algebraic equation with 6 variables in it. So if we know any 5, we can find the 6th variable. What's the final pressure? If a 10-liter sample of carbon dioxide at 300 Kelvin and 1 atmosphere is changed to 20 liters at 600 Kelvin. So I do the same thing as before. P1, V1, T1, P2, V2, T2. I try and pull all the variables out and just get the numbers away from the words so I can work with this and do the algebra. So what is the final pressure? So P2 is our unknown. And we have 10 liters in our sample. So V1 is 10.0 liters. It's at a temperature of 300 Kelvin. And it's at 1 atmosphere. Make sure when you write down the 300 and the 1, you put all the sig figs in there. Now we're changing it to a volume of 20.0 liters. And my new temperature is 600 Kelvin. So P1 V1 over T1 equals P2 V2 over T2. I want to get the P2 by itself, so I multiply both sides by T2 and I divide both sides by V2. So P1 V1 T2 over T1 V2 is equal to my new pressure. Did you have a question? Okay, you're ahead of me. So we plug in the numbers. My P1 is 1 atmosphere. My V1, 10.0 liters. My T2, 600 Kelvin. Divided by T1, 300 Kelvin, times V2, 20.0 liters. So my new pressure, P2, is equal to 1 atmosphere. Now, does that seem a little odd to you? Exactly. Until you think about it and you look at it and say, wow, what did I do here? My temperature doubled, so I have 600 over 300, and that's 2. And then my volume doubled, but it's inverse, so I have 10 over 20. So it all cancels out, and we actually have no change in pressure. So you really need to pay attention to these. With the smaller gas laws, I think it's easier to decide, should my number be bigger or smaller, because it's either directly or indirectly proportional. It's harder with this one. Okay, let's have you go ahead and do this on the boards with your groups.